We will continue our discussion on discretization on lecture 12. What we are essentially going to do is display the various concepts by taking up an example of 1D convection equation. This is the most elementary equation that one can talk about. However, we would note that discretizing this simple system 1D convection equation, which is an example of a non-dissipative, non-dispersive system of solution, that we will see that various discretization method actually adds dissipation and dispersion. So, we will be talking about this in some details. This will be followed by our discussion of discretization using operators. This will essentially simplify our expansion methods of differential equations and integral equations, and we will develop generic method of differencing, and specifically for our application for this course we will talk about symmetric or the central schemes that we talked about in yesterday's class, but we will focus our attention on higher order representation, because we are interested in scientific computing. So, we require accuracy, and the accuracy would be somewhat related to higher order for explicit schemes, and such schemes, when they are performed in a central manner, does not function always well, and that requires that we use asymmetric stencil, and this is what we talked about as upwinding in the last lecture, and in today's lecture we will show that the upwinding is nothing but a blend of a central scheme using higher order stencil along with a higher order even derivatives. This two together consist of upwinding. After the class, someone came up and asked me that if we use the central difference scheme for discretizing the first derivative in this equation, why do I say the solution is going to be dispersive? That is the question. To clarify that doubt, what we do is we look at the following two steps. First, we have the continuum equation. From there, we come to the discrete equation. So, let me write this part. Let us say it is discretized at a node j without any questions asked about its accuracy. So, let us say the time discretization is accurate, and this is what we write. And let us say we do this space discretization using forward difference. So, let us also look at the case for which C is positive. So, if I do a forward difference here, I will be doing this delta x, that is what we would be solving, right. So, now, so this is one step, you come from differential equation to difference equation. Now, to understand what you are doing, what you can do is write down the Taylor series of this term and observe what is the equation that we are in essence solving. So, if I do that, then u j will cancel, and then I will have delta x del u del x and so on and so forth. So, this is what we are doing. So, the first step is from differential equation to difference equation, and trying to understand what we are doing, we go to again an equivalent differential equation that we are handling numerically. That is what it means. If numerical operation amounts to taking the step 2, that is equivalent to corresponding differential equation of this form, and if I do it, then of course, this I will get as C du dx, okay. And this additional term, that will be C delta x by 2 and so on and so forth. So, that is equal to 0. So, in a sense, what we are doing is that is what I would write by looking at the terms which belong to the parent equation. So, this of course, is evaluated at j, everything is evaluated at the jth node. So, by discretization, we are in a sense solving this equation and every other term being pushed to the let me write like this triple x, okay, and so on and so forth. We will have many more terms. So, when we decide to solve this equation and we adopt this algorithm, that is equivalent to solving this equivalent differential equation. Now, what you are noticing that ideally you would like the right hand side to be equal to 0, but the discretization forces you to solve an alternate equation where the forcing comes from this set of terms. Now, looking at that expression immediately will set the alarm bell ringing. What is this term? This is a second derivative term, but with a negative sign, and C is positive, right. So, this is going to give you some kind of a anti diffusion. So, it will not attenuate the solution. What it would do, that if you adopt this method to solve this equation, you are going to get into trouble, right. Now, why did it happen? Well, it is very easy for you to comprehend this scenario by looking at an analytical solution. Let us say if I have a solution which is at t equal to 0 like this, at a later time this solution should have just simply bodily shifted itself at a speed c. That is what that equation means. Now, that means what? The information is propagating from left to right. So, if the information propagates from left to right, what we have tried to do here? See, we are trying to find out the information at the jth node, but how do we develop that information? By looking at what the function is doing at a point to the right. So, we have violated physics here. The information should have gone from left to right, but your numerical method adopted tells you that it is going in the opposite direction, and that is the reason for this. So, this is of course is wrong. You should never do it, right. You got to follow the physics of the problem. You cannot just mindlessly plug in some mathematical expression without thinking what is the consequence going to be. What you can do? Well, prescription is this, that instead you follow the physics. So, you know the information should go from, if I am looking at the jth node, I should get the information from j minus 1, not the other way around. right. So, what happens is I should do this, and this without even analyzing I could just simply write it like this, but if you are not convinced, you follow the train of thought that we have written it down here. So, what would we get? This will be plus, this will be minus, this will be plus, this will be minus, and so on and so forth. So, what you are going to get is this will be like this will be minus, and this will be plus, and so on and so forth. So, what happens is then you will get a plus sign here. So, what happens in this case, if I do a backward differencing, that is this second formula, if we adopt that, that does not violate the physical principle as such in terms of information propagation, because it is going in the right direction, it is going from left to right. However, taking that particular stencil for the first derivative amounts to having this kind of terms on the right side. And you do understand that there are whole lot of terms there. The one which will dominate the dynamics would be the leading term, because everything is proportional to this grid spacing. So, if the grid spacing itself is small, so you could see that the higher derivatives would trail off in terms of their importance. The leading term would be, of course, the leading truncation error term, and that is what we also call as the truncation error itself. So, the truncation error always refers to the leading omitted term, not necessarily the whole set, because that is too unwieldy. Now, what you notice that as far as information propagation is concerned, directionality is maintained, but we have this problem of attenuating the solution, because we are adding a dissipation here. So, that is something we should be worried about. So, maybe in this case we will go properly in the right direction, but we would see that as time progresses the amplitude will keep coming down. And we are again not commenting upon if there is some effect of dispersion in the process, that we will be doing shortly. We will show which method gives what kind of dispersion. However, you understand that taking a first order accurate method by the forward difference violates physics of the problem and should never be attempted. Taking the backward difference form, it does not violate the directionality of the information propagation, but it surely does attenuate the signal, and that is something we should be worried about, right. So, we should not add on numerical dissipation. So, this works like a numerical dissipation. Physically there is no dissipation in this problem, but solving it by backward difference formula is equivalent to adding a numerical dissipation, right, because it is proportional to delta x. In the theoretical limit of delta x going to 0, it should have gone away, it should not have bothered you at all the right hand side terms should disappear. Now, so having noticed that both these methods have something bad about themselves, now what we could do is look at the third alternative that we are investigating there. So, here what we would do, let us say we do this, and we have already noted that this is higher order accurate term, in the sense that you can write down the Taylor series expansion. What would you get? The odd derivatives would disappear, right, is not it. So, uj will go away, the first two derivatives, sorry, that will remain. So, I will get this C by 2 delta x, uj goes away. So, I will get 2 times this, and the second derivative goes away, and I will get what? I will put that term, right. So, of course, what you are noticing that this is equivalent to solving this equation. This 2 delta x will go away, and this is what we are doing. This is again evaluated at the jth node, and this term goes to the right hand side. So, what I am going to get is c delta x square by 6, and this is my leading omitted term. So, that truncation error is not proportional to the second derivative, but now it is proportional to third derivative, right. And this is what I noted in the last class, that this brings in dispersion. Now, the question arose, I think he is missing, whoever asked that question today, he is missing today. Why do we say it is a dispersion? That is the question. Why do we call it a dispersion? I am not asking to remember some kind of a mantra that all odd derivatives are dispersion, even derivatives are dissipation, but we should be able to rationalize why do we call it dispersion. Yes, Abhishek. No? Why, how should we say that it is dispersion or dissipation? Anyone? I mean, we spent about 4 lectures talking about waves. That is all about that, to make you familiarize what are these basic physical processes. Shakti, why do we call it dispersion? How do we nail it? Yes, it is indeed dispersion. No? Okay. I'll give you a clue. What you do is you try out your so called trial solution, right, some amplitude times let us say e to the power, plug this in your, yeah, that is what we are doing. We are looking at a Fourier harmonic, plug it in there, and then you would develop an equation between omega and k, right, isn't it? That is what we have done for so many days over the last couple of weeks. What I would get then, so del u del t term will give me I omega u naught. I am omitting the phase part, and this part will give me I k c u naught, and what do I get on the right hand side? The leading term will give us c delta x square by 6, and if I take the third derivative, then I will get this, right. So, of course, you can knock off, there will be u naught too. So, you can remove this, and I can go away. So, we will get minus I plus I k c, and on this side we will get k cube. Yeah, I square will take care of that. Right. So, what we get here then omega equal to I k c minus, well, this I will not be there, all the i's will go away. So, omega equal to k c minus k cube c delta x square by 6. So, you have omega as a function of k, and how do you find out it is dispersive or non-dispersive? We calculate the group velocity. If the group velocity happens to be the same for all k, then we know it is non-dispersive. If group velocity is going to be dependent on k, that means different k component will transmit its energy at a different speed. So, if I have a compact disturbance at t equal to 0, it will disperse itself. So, you can work it out and you can judge for yourself why we call that as a dispersion. Is that clear? If that is clear, you can understand that we now have at our disposal tools to understand what we do numerically. It's and we can observe their potential in solving some given equations. Well, I think we started talking about other ways of looking at discretization. The alternative was here, if we try to, let us say, do a polynomial fit locally and use the function values at discrete nodes, then we can fix this coefficients A, B, C in that polynomial representation. Yes.
There is a central difference method. So we are predicting uj plus 1 and we are at uj. So I mean this does not violate the principle of physics, like we are moving from left to right.
Yes.
So we are predicting uj plus 1.
No, we have written everything at jth node, you see, that is what it is.
So the problem in the first, the forward was that we wrote uj plus 1 minus uj. That was the problem, right? And here also we are writing uj plus 1.
But look at it. It is symmetry. The symmetry of this with respect to this cancels out those information, right. That is what actually happened. Okay. So, eventually what happened is this. We look at this. What happened as a consequence for the forward difference case was an anti-diffusion that led to numerical instability, but here there is no such thing happening. What is happening? Here again you write that we are not being truthful, because that is the price we pay for discretization. Differential equation always gives you a point property, and whenever we discretize, we are getting in information from the surrounding point. So, in the hope that delta x going to 0, all the surrounding points would collapse into the point in question. But at the same time, we need to understand what happens to our numerical procedure. The numerical procedure should not lead to some kind of self-sustained instabilities. That is what happened with forward difference, but in this case it does not. But instead what happens, instead of amplification of numerical solution, you are generating spurious dispersion. That is what you see. If this part was not there, then d omega d k is equal to c, that is a non-dispersive solution, that is what you wanted. But now because of this k cube term being there, you will see the group velocity is becoming a function of k, and that is the price you are paying. So, I am not for any moment suggesting that if I ask you to solve this equation, adopt this. All that we are doing, we are now able to analyze and say what algorithm gives us what. So, this also is a faulty one, because this is going to lead to spurious dispersion. The physical solution does not have this, right. Okay. Now, coming back to this, suppose we decide to fit a parabola, we can do any order polynomial that we want. If you want to fit a cubic, then of course, you will have to fit it with respect to 4 points, but let us keep our ambition modest and try to fit a parabola here with respect to fi plus 1 and fi plus 2. And if we do that, and we can shift the origin to xi. So, if these points are spaced at a distance h, so xi plus 1 is at h and this is at 2h. So, basically I will successively plug in f of xi would correspond to this x equal to 0, f of xi plus 1 will correspond to x equal to h, and f of xi plus 2 would correspond to x equal to 2h. So, we did that and we got these 3 equations, we did solve them and we got these 3 values. So, once you have that polynomial expansion, you could calculate the derivatives. So, what you have here is a bit of a advantage, because you are going to get both the derivatives, right, the first and the second derivatives at the node I. if I look at this, so we are basically following the same kind of strategy. We are trying to get the information at the ith node in terms of the information obtained from I plus 1 and I plus 2. Now, you see this kind of artifice of trying to generate information from one side alone is sometimes is unavoidable. Why? Because let us say if I am trying to solve a problem in a given domain, then I do not know what is outside the domain. So, if I am looking at a point on the domain, I have to get all the information from inside only. So, I cannot do that this kind of thing, central difference. If J happens to be the boundary node, so if it happens to be the left boundary node, then I do not have this, and if J happens to be the right boundary node, I do not have this. So, your hand will be forced to adopt one sided. And this is a major issue, it is not a trivial issue. In fact, satisfying boundary conditions happens to be Achilles heel for all the computing people. I mean, this is not a problem which has been equivocally answered by anyone. So, we do actually look at specific problem and we do sort of series of investigations. We try to understand how this happens. I will also tell you there are some approaches which tries to invoke physics and get boundary condition information, but it is not necessarily easy. Okay, one thing you noticed that we wrote down the first and second derivative at I, but since you have the polynomial expansion, you could have used the same thing for I plus 1, right. Then that would be equivalent to your central difference kind of formula. So, you are generating information at I plus 1 in terms of I and I plus 2, or you could have used that expression to get information at I plus 2. So, that would be like your backward difference, right. So, what we have written here is like a forward difference. We could do it by use the same thing as a central difference as well as backward difference. So, there you have it. This looks all bit of ad hoc thing, right. I will have to juggle and struggle with all this polynomial plug-in points and so on and so forth. So, mathematicians have tried to formalize it by using operator notation, right. So, suppose I have a sequence of points for the independent variable x located at n, I will call the dependent variable y as y n. Then we can define some of these operators, like the forward difference operator would be something like y n plus 1 minus y n. The backward difference operator, we could write it as y n minus y n. The central difference operator, you notice that it is half a point to the right, half a point to the left. Well, we could also do it integral points, but then what happens? The accuracy depends on delta x. So, if I instead of taking delta x, if I take delta x by 2, my accuracy will improve. So, that is the motivation by taking this half node points to the right and left in defining this. As I told you, we could also adopt integral node values, then you realize that I may have to divide it by a factor of 2, because that is the distance between the extreme nodes, right, 2 delta x. Now, we can also bring in what we call as an averaging operation. So, averaging operator is mu. That means that you are taking the function values to the left and right and average it with equal weightage. Okay. Now, given a point y n, I could write y n plus 1 as if some shift operator E is working on it. That is the definition. And the same way, if I do an inverse operation E inverse, then I go to the point on the left, right. And this is something you all know, you have done it n number of times, differentially of operator D. Now, we can actually play around with all these operators and definitions and see if we could get something meaningful out of it. For example, the forward difference operator here is defined as y n plus 1 minus y n. Y n plus 1, I could write it in terms of the shift operator E of y n. So, basically then this forward difference operator operating on y n is equal to nothing but E minus 1 operating on y n. So, delta is E minus 1. So, this is simple. Same way, I could write down the backward difference operator, right. So, this corresponds to actually y n minus 1. So, that we have written as E inverse y n, and that is what gives us this. Now, mu was the average, where you have taken the point shifted half to the right and half to the left. So, shifting half would be equivalent to e to the power half, and shifting half a point to the left would be e to the power minus half. So, that is your mu operator related to the shift operator. So, you can square it, and this is what you are going to get. Now, I think there is a mistake here. This is delta 1, right. This delta 1 is y n plus half minus y n minus half. So, this is delta 1. So, this should after squaring we should get that, right. We should get that. So, if delta square is this and mu square is this, you can relate mu and delta. The essential idea that we are trying to derive benefit from is to obtain some kind of one kind of operation and try to generate information based on them for the other operators. For example, if I write a Taylor series of a function about f x for its neighbor x plus h, then of course, you write this in terms of the Taylor series, and you note this f prime of x, well, this all should have been within parenthesis, they actually refer to d of f, right. So, this will be d square, this will be d cube. So, it effectively occurs like this, right. So, what you notice, the quantity within this bracket is nothing but e to the power h d. So, what happens is we can write e equal to e to the power h d, or take log and define d as 1 over h ln of e. And recall in the previous slide we had related e with delta. So, e is 1 plus delta. So, if I do that, then I get d is equal to ln of 1 plus delta by h. The same way I could have also written in terms of the backward operator, that would be ln of 1 minus delta by h. So, basically what we are trying to do is obtain say expression for d. We are obtaining the expression for d in terms of either the forward difference operator or the backward difference operator. And since you can write out expression for ln of 1 plus delta, you can actually get this. So, this is a much more neater way of obtaining the derivatives either in terms of forward or backward operator, provided you know what this delta is, and if you know what delta is, you can get this, and you can actually derive formula of higher and higher accuracy by including more and more terms, right. So, for example, if I just keep the first term, then I would have gotten the forward difference operator that we had written. So, if I retain the first two terms, it is going to be a higher accurate formula, because the omitted term would come from now delta cube. So, that would be giving you some second order accurate formula, right. So, you can actually take one sided formula and obtain higher accuracy representation by taking either this 29 or 30. So, that depends on where you are looking at. So, having formally obtained the expression for D in terms of those forward or backward operator, you could get any derivatives, right. So, if say for example, I am looking for the kth derivative. So, that is d to the power k operating on y, and since I have d as a function of let us say delta, I could take that whole series and raise it to the power k and simplify. This is what we are going to get, right. Now, once again I suppose there would be a factor of 2 coming here, the factor of 2 coming here, because these are based on integral nodes, right. So, this delta 1 we have defined as y n plus 1 minus y n by 2. So, that 2 is missing. So, there is a mistake here, I will correct it. Whereas, the central difference operator based on half node is delta, that is given here. Since we have already established E is equal to e to the power h of d. So, I could plug this in here and write delta in terms of this, right. So, e to the power h d by 2 minus e to the power minus h d by 2, I can write it like this. So, the quantity within the square bracket resembles that sine hyperbolic function, right. So, that is what we get, and in terms of integral nodes we could write this, and I suppose there is a factor of 2 missing, then this 2 will not be there. And what happens is then we could write the central difference operator as 2 times sine hyperbolic h d by 2 or delta 1 in terms of, please ignore this 2 part, the sine hyperbolic h of d. So, what I could do is then from here I could write d as 2 by h sine hyperbolic inverse this quantity, and you look up any mathematics handbook, you will find out they will happily give you all kinds of series expansion for the sine hyperbolic inverse function, and that is what your 32 is. 32 is nothing but this expression. So, what you have gotten here is this. So, this is an alternative form where you are getting the first derivative in terms of only central differencing, right, because these deltas are the central difference operator, these are not one sided. Or you could write it in terms of those integral node values, then you would have delta 1 and then you can write this. So, these are formal ways of simplifying your task and getting as high and accurate formula that you want. Now, well, I mean those are very nice. I could have gone back and done what we are trying to do here. If I want to, let us say, obtain formally higher order, let us say 6th order accurate stencil for say first derivative, you realize that most of the time your governing equations usually have the first derivatives and the second derivative, right. You look at any branch of physics, at the most you will get biquadratic, right, 4th derivative. So, we will try to get some of those expressions explicitly, and we have also realized by now that we can derive higher accuracy by taking higher order formula, and that is what we are trying to do. So, our basic aim is to obtain a first derivative which will be of 6th order accuracy. At the same time, we would like to do it like central differencing, right, because we have seen if we try to do one sided, we have to be careful, because we may like to add numerical dissipation, but in the process we have seen that it could instead add anti-diffusion, right. So, one of the safest way in computing is always try to begin with symmetric operator, symmetric stencil, so that you do not add either dissipation or anti-diffusion. Both the cases are bad. If you add dissipation, it is going to damp out the signal, and if you of course add anti-diffusion, you do not have to worry, the code will blow up on your face. You will know that you are wrong. The problem is the other way. The problem is when you have a working code, but the solutions are wrong. Unfortunately, that is the story of all commercial software. They are all wrong, most of them are, and because they unphysically attenuate the solution. So, to avoid that pitfall, it is always better that you go to a symmetric stencil, and if I want to write a symmetric stencil, what have we seen so far? That the first order accurate formula for that first derivative involved 2 points. Second order accurate formula required 3 points, right, j plus 1 and j minus 1 if I am trying to find out at j, right. So, if I extend the logic, so sixth order accurate formula would require 7 points. If I am looking at, let us say, the ith node, I will take, excluding that ith node, I will need to take 3 points to the left, 3 additional points to the right. And if I club them in this clever manner, then what do I notice? All the even derivatives will disappear because of this minus sign, you see, f I plus 3 minus f I minus 3, f I plus 2 minus f I minus 2. So, we are trying to develop an expression where we do not want even derivatives to be there, because they can do both the things that we have talked about. So, we would club them like this. Since the coefficients are 1, so all those even derivatives go away and expand this right hand side, and on the left hand side we have only first derivative, right. So, if I look at the first derivative, I do not know why I mixed it up with I and n. So, this could be I. So, f prime I, left hand side coefficient is 1, and on the right hand side what do I get? From here I will get 3 h into the first derivative, and there are 2, one coming from here, one coming from there. So, that is what I have 6 h n, right. So, this combination will give you everything, factor of 2. So, I have taken that 2 out, right, and the lead term has h there. So, that is what we are getting. So, this will give me 3 a, this will give me 2 b, and this will give me c. So, that is what we are getting. And the higher derivatives, of course, they will be 0, right, there is nothing on this side. So, the third derivative is 0, whereas the right hand side gives me this. So, what is this? This is 3 cube, this is 2 cube, this is 1 cube, right, and this one is 3 to the power 5, 2 to the power 5, 1 to the power 5. So, you can see a very neat order there, and we are trying to fix this 3 unknown coefficients a, b and c, right. So, I just stop here, because we have adequate number of equations for these 3 unknowns, and you solve them, and this is what you get, right. So, this is your sixth order accurate formula, which will involve I plus 3 to I minus 3. You also notice one interesting feature of this formula. Looking at the formula, you can tell that this is a non-dissipative formula. Why? There is no term involving f I. If there was a term involving f I, then you are sure there is some dissipation involved in this scheme. See, that is what we have done. We have not included in f I term to keep the even derivatives away, right. So, that is what you are seeing here. So, this is what you get. So, if I am saying it is a sixth order accurate, so what is the leading truncation error term? That would be proportional to, that will be proportional to the seventh derivative term, right. We have stopped here at f 5. So, the next term will be f 7. So, as far as the polynomial expansion of 34 is concerned, it satisfies exactly a sixth order polynomial, right, because we are fixing a and b and c by equating the right and left hand side. Anything that is unbalanced is at the 7th derivative. So, that is why we call this as a 6th order accurate method. Yes. What I did on the right hand side, I just simply wrote a Taylor series. So, we are writing the Taylor series about the node ith node, right, because the left hand side the first derivative has at the ith node, right. So, once you do that, you are basically equating the coefficients on either side, and once you have 3 equations, 3 unknowns, you solve them and this is what you get. So, this is a 6th order accurate stencil for first derivative. Now, what happens? Suppose I would have tried to do that with a 4th order accurate stencil, then of course, this A is superfluous. As I explained to you, a 4th order would involve 5 points, 2 to the left, 2 to the right. So, we should have begun with B and C, and once we do that, this is what we get, right. So, even this is unnecessary. This is unnecessary, and then we equate this to fix this 2 constants B and C by equating the coefficients of f prime and f triple prime and solve them, you get this. So, this is your 4th order accurate expansion for the first derivative. Again, this is a non-dissipative formula and symmetric stencil. Now, this is something I would first derive it and then I will explain why we are doing this. Let us say we are trying to find out an expression for the 6th derivative term. So far we have been looking at the first derivative. So, let us try to derive an expression for 6th derivative by using symmetric stencil. Now, 6th derivative means it is an even derivative. So, if I want to write a symmetric stencil, what should I do? I would again club them, and not only the points should be there, they should be also in equal proportion. So, if I have f I plus 3 and f I minus 3, look at their coefficients. Coefficients are the same. So, I cannot write 2 f I plus 3 plus 3 f I minus 3, that will not be symmetric, right. So, symmetry requires these coefficients to be same, and that coefficient has been brought out here as a, b, c, etc. Okay. And the point that I made, that if I am looking for even derivatives, I should have to have the point itself, the point itself. So, d into f I. Now, you also notice that we are interested in looking at the even derivatives. That is why the intervening sign are now all plus. First derivative we did it like couple them with a minus sign in between. Now, we are putting all of them with a plus sign. So, when we add this up, what will happen? The odd derivatives will disappear, and all you would be left with the even derivative terms, including the function. So, if I look at that, the function value f I has of course d coming from there. From here I will get 2 c, from here I will get 2 b, and from here I will get 2 a. That is your first equation. So, this is the f of 0. Now, the second derivative term of course will come from each one of them except the d term, and this is what we get. So, we have 4 unknowns. So, we stop at 7 and we can solve for this a, b, c, d and plug it in there. So, that is what I observed, that if I am looking at an expression for the even derivative by symmetric stencil, you will notice that the coefficients have to be same. So, this is plus 15, this is plus 15, this is minus 6, that is also minus 6, and this plus 1, the last one is plus. Okay. and the d is of course standing out by itself, that is minus 20. So, this is what we do. This is what we do. Now, you should ask why all this gymnastics that we are doing, but before I do that, I will just simply conclude this part, that if I am trying to find out an expression, let us say for now not the sixth derivative, but the fourth derivative, we will go through that same exercise again, okay, and look for 3 equations for 3 unknowns, solve them, and this is what we get.
So, the derivative expression be anticipative?
We are just calculating the derivative itself. Now, it depends on how you use it in your difference equation. If you use it, keep it on the right hand side and keep it with a plus sign, that will be a diffusion term. If you do it a minus sign, that will be antidiffusive, right. So, we are getting the expressions and giving you the degree of freedom to choose the way you want to use it in actual equation. Okay. So, now why we do what we have done? I mean, why did we do all this? Well, whatever we have here on the board, we can make use of it and see what we are doing. Now, let us say if we would have done this for that equation, then well, we would have gotten term like this, right. And what we find that this is antidiffusive, and if I instead would have written it like this, then I would have gotten a similar equation like what we have here. So, you see, sometimes taking one sided stencil and let us say here what we have here is a first order accurate expression is equivalent to solving the given equation by having some next higher order even derivative. So, this was a first order accurate method. So, that is equivalent to solving this equation, actual given equation, plus a next higher order derivative. So, it was first order method. So, it was you have a second derivative appearing there. So, this is a simple equation, right. In your actual application, what you would be doing is a complex equation, maybe with the second derivative, first derivative term coming, there would be with the nonlinearity, so on and so forth. So, this was a simple constant coefficient linear equation, and we are seeing this, that solving this method by let us say an odd order accurate method is equivalent to solving the actual equation and spiking it with the next higher order dissipative term, right. So, then we have seen that if we develop a method, let us say we will show it in the next class perhaps. What we find that solving it by let us say a central method leads to some kind of a numerical instability. So, what we can do? if we know the method is numerically unstable, we can try to stabilize it numerically. And how do I stabilize it? So, the amplitude is growing because of numerical instability. So, I would add some dissipation, right. How do I add dissipation? We have seen this first order upwinding is equivalent to adding a second derivative term. In many physical problems, you will find that the governing equation already has second derivative term. Then is it safe to add second derivative term for numerical stabilization? The answer is no, because you are then going to alter the physics of the problem, because physically itself there is second derivative term. So, what you may like to do is numerically stabilize those cases adding higher derivative terms. So, I would not add second derivative term, but I would add let us say fourth derivative or sixth derivative, and that is what we have been trying to do. We are trying to find out expressions for say fourth derivative here, or in the previous case we are trying to find out the sixth derivative here. So, what I would do, I may decide to take a symmetric stencil for let us say the first derivative, but application of the symmetric stencil on the first derivative gives me a method which is unstable, numerically unstable. So, what is stable, what is unstable, we will discuss it in the very next class. Then how do I rectify? The rectification can come through by selective explicit addition of even derivative term, and when you do that, this is what we call it as upwinding. Basically, we are creating a proper bias to the solution, okay? And that is what we will be talking about in the next class. Okay?